Welcome to this tutorial on the function of a function rule. Now the tutorial assumes that you have already met the chain rule, but what we're going to develop in this tutorial is a very quick and efficient way of applying the chain rule, which for the purposes of this tutorial I'm calling the function of a function rule, but really a function of a function rule and the chain rule are exactly the same thing. Now, before I begin, I'd like to have a go at the starter problem yourself using the chain rule. I'd like to pause the video now and give that a go. Okay, so using your knowledge of the chain rule, you should look at this expression, and we should look at assigning some letter to that, say u, and we'd communicate this by saying let u equal 3x squared plus 1. So now our equation is simply y equals u to the 8. And what I like about both of these equations is they're now very simple to differentiate. In fact, really that's just a core 1 skill to differentiate both those equations. So let's do that. So here we get du by dx equals 6x, and here we get dy by du equals 8u to the 7. Now of course ultimately we don't want du by dx or dy by du. In fact we don't want u at all. That's a third variable that we introduced ourselves. But this is where the chain rule of course comes in handy, because the chain rule implies that if we want dy by dx, we can say that's equal to dy by du. And if you look at the chain rule now, I'm looking at the du and thinking I don't really want that there, because that's not going to give me dy by dx overall. So that's why a du is fixed there, in order that we get that cancellation. But in order to get the dx, of course, I need to have a dx there. So that's how we string together the chain rule. Okay, well we know what dy by du is. We can see that's 8u to the 7, and we know what du by dx is. We can see that's 6x. So essentially what I need to do is multiply these two terms together. That's what the chain rule is implying there. So we can see we're going to have 6 times 8, which is 48, and then we're going to have x times u to the 7. But instead of putting u, we can revert back to now what u actually is, which is of course 3x squared plus 1. So let's put in now that u is 3x squared plus 1, but now looking up here, we can see we need to raise u to the 7, so we do that there. Now at this stage I think it's worth looking at what the original equation was and what its derivative is, and looking at the similarities. For example, we can observe that we have a 3x squared plus 1 there, but also that's clearly present in the answer. Other observations could include the fact that we've got an 8 there, and as is often typical with differentiation, the power has been reduced there. Perhaps it's unclear immediately, it's not immediately obvious how the 48x gets formed, but perhaps by looking at what's happening here we can spot a more general rule for what's going on. And to investigate that, let's just try and generalize what's going on. So consider the following. Okay, let's do that here. Let's try and generalize what's going on. So we have y equals some expression I've highlighted in green there, to some power. That's the sort of structure that we have there. So I don't know what the expression will be. I will just say it's some function of x, say. But whatever that expression is, what we seem to be doing is raising that to some power. And let's see if we can work out what we would get there. Well, just trying to follow through on the normal strategy, that would be to let u, say, equal f of x. Therefore, we would have y equaling u to the n. And what we'd normally do is differentiate both of them. So here we'd get du by dx, which is, well, there's f of x, and we need to differentiate that. So I suppose what we'd get is the derivative of f of x. And here we'd get dy by du equal to, now, mistake, apologies, let me just rectify that. That's dy by du. Of course, we're so used to writing dy by dx. It's important we put a u there. This is dy by du. N we're treating as a constant here, so that comes down, and we have the u, and then we take 1 off the power there. And now, of course, I'm trying to work out dy by dx as normal, so we use the chain rule. The chain rule implying that dy by dx equals dy by du times du by dx. And let's just plug in what we've got here. So dy by du is n times u to the n minus 1, and du by dx is f dash of x. And if we could just tidy this up a little bit. Now u is, what was u again? Well, u we just said was f of x here. So we can replace that, and I think it might be quite nice to put the n first, then perhaps the f dash of x, and now u is raised to some power, but what I might have to do there is put the u, which is f of x, in brackets, and put the n minus 1 there. So what we've actually done here is develop a general rule. Here in green we have our function, and you can see that we still have the function there in brackets. But now, of course, 1 has been reduced from the power. It was n, it's now n minus 1, as is the case normally with differentiation. As normal, we can see that n goes to the front, but also the difference is now that we also have the derivative of what was inside the bracket appearing there as well. So this will always happen when we have this situation. So what we've got here is actually a quicker rule that we can follow that will prevent you doing all of this sort of work here. And in fact, you can just go in one line from there to there with practice, saving all of this work in the exam. But if you're going to do that, I think it's really important that you practice lots of questions, and you practice the technique, which is what we're going to do a little bit of today. Okay, here I'd like you to state the rule a bit more formally and in a slightly nicer way. So what we've got here is some function, but of course we're raising this function to some power n there. And if you spot that situation, then you can always just follow these 4 steps. So we bring the power down, n, but we also multiply the power by the derivative of the thing inside the bracket. So whatever f of x is inside those brackets, the derivative gets pulled out and it multiplies the n there. But then we just write down what we normally get, so whatever, apologies for that. Try that again. So we write down f of x as normal, that appears there, that's step 3, and finally we just subtract 1 off the power. So with practice you will get very good at applying that rule, and it's really very important actually if any of you want to go on to study further mathematics at university. You need to be really very good at differentiating these composite functions very quickly. It is good to sometimes do a formal chain rule, but in simple cases you really want to be differentiating very quickly. So consider this example. Let's think about how we would differentiate this. Now, first of all, I sort of drawn to the fact it's a fraction. I don't particularly like that. It sort of makes it more difficult. So of course what we could do is rewrite this so it's y equal to, and let's take this bracket, and because I'm essentially writing this on the numerator in the wrong place, if you like, I compensate there by saying that that is a negative power. Now I'm in a position to apply my rule, so I can just differentiate this pretty much in one move. So dy by dx will be, remember there's 4 steps, I hope you can remember the 4 steps. Of course step 1 is we visualise the power coming down, which should be familiar to you, because that's generally what we do in differentiation. So this power goes down, that's step 1. So we get a -2 there, but then the derivative of whatever is inside the bracket, we need to differentiate that, and that comes out of the bracket, so we get 4x cubed there. So we just times here by 4x cubed. I'll simplify this on the next line. Let's just focus on getting things correct. The third step is you write the bracket as normal, and then we're almost there. You just need to subtract 1 off the power. Remember, you're starting on -2, so we go further into debt if you like, so that will land us on -3, and we've differentiated it. Of course no one would leave it like that, it would be terribly bad form to leave it like that. So let's tidy this up a little bit. Well, here you can see we're going to get -8x cubed, and I can write that on the numerator. And again, this power of course is really saying that that expression belongs on the denominator, which is of course where we should now choose to write it. And we've differentiated it, and that saved us some considerable time applying a formal chain rule. And you know, with practice you'll find that you get very good at this, not least because most of the steps are familiar to you. It's perhaps just this extra step here where you need to pull out the derivative of what's inside the bracket. That's the difference to questions that you may have done before. Let's look at another question. So I've got example 2 here. So we could you know, make some substitution here, let u equal what's inside the bracket and do a formal chain rule, but we can just do it directly. Dy by dx will be, let's follow the rule. Now that 6 is fine there, you know, that will just appear in my answer here. I need to focus on step 1, which is of course to bring that power down. So you can actually see that you'll have a third times 6, which I think we should just do straight away. 6 times a third is of course 2. Now that's step 1. Second, the derivative of this expression we need to write next. So we then differentiate that. That'll need to go in brackets, and we get 3x squared subtract 9. And step 3, we write the bracket as normal. And the final step, which we generally do in all differentiation, is to subtract 1 off the power. Perhaps oneness we can think of here as 3/3, which will land us on negative 2/3. And then we look to tidy. You may possibly observe the fact that there's something obvious to pull out here, so I think that would be good form if we did so. So on the numerator, pulling the 3 out there of the yellow bracket, we will have 6 once the 3 has been pulled out, x squared minus 3. And I was thinking for 1 second we could have the difference of 2 squares there, but 3 is clearly not a square number. And again, we've got a negative power, which is really communicating to us that that expression belongs on the denominator. It's in the wrong place, so let's write that here. And that's to the power of 2/3. So, that's a fairly complicated example, but even so, it's really quite easy to use the function of a function rule once you've had some practice. Now, what I have for you here is just, I think I've got 7 questions. These are questions I normally use with my classes. You can see there's 2 questions on each slide. What I'd like to do is just have a go at them, and I will reveal the answer step by step. So pause the video and just have a little go at the problems. So there we've got the solution to question 1. And if you'd like to have a go at question 2. A bit more complicated there for the extension question, as you can see. This often can confuse students. If you wish to write what I've highlighted in yellow on the numerator, you can. It just means it will now be a negative 3, but please leave the 5 where it is. It belongs on the denominator. That's where it should be. Don't take 5 along for the ride as well. Question 3. Okay, so obviously there you would choose not to use the sort of square root symbols there. You'd want to use the fractional powers. Have a look at question 4. Let's look at the answers there. So the extension question, as always, looks a little bit more interesting. And I think what's quite interesting to note here is in this bracket, we have 2 as a common factor, which of course we can pull out. But as we pull the 2 out, because we are squaring this bracket, as 2 gets pulled out, it actually becomes a 4. Now you might be thinking, why didn't put a 4 there? But of course that's because the 4, one of the 2's from the 4 cancelled with the 18. Question 5. Okay, so that simplifies like so. Just thinking here, we do have the difference of 2 squares. So yeah, I mean, you possibly could have done something there, but it's to the power of 3 over 2, so perhaps not. But we should always look to see if we can simplify things down. Question 6. Let's just see if there's anything of particular interest there. Yes, I mean, again, you should always try and simplify it as you can. You can clearly see that 3 comes out of that linear factor. So that would be good practice to pull the 3 out, which is why that then becomes a 6. And finally, question 7. And there's the solution there. You'll notice something quite subtle on the extension question there. First of all, the 3 belongs on the denominator. I hope you got that bit right, but it should have really been minus times this bracket, but all I've done is sort of taken the minus in and swapped it around. And that saves you putting a minus in front of the fraction. It's far neater just to feed the minus through this linear factor here.